In this section, we're going to be looking at a physical application that has differential equations are used to solve it. So in this situation, we have a spring is attached to some sort of a support. So we'll see something like this. Yeah, it's just one of those curly springs. So here's your support. That support is non-movable. It's rigidly supported. Here's our spring. And right now it's just hanging with nothing attached to it. So it's not being stretched in any way. So I'm going to refer to its length as lowercase l. Now, add a known weight. So this thing now, with a weight attached, will be stretched out some. I'll constantly be referring to this thing as a mass, because that generally is how we'll be looking at. And so now I'll call it the letter M. So here's my weight, or mass, whatever you want to call it. Stretches the spring out. And recall its length, its normal length, only went from here to here. And then I've got stretch. The amount that it goes beyond its normal length is referred to by the letter S. So S is the stretch. S is the stretch, or the length of stretch. And Hooke's law, part of Hooke's law says this. That tells me that the force equals some constant times S. F is for force. K is a constant. In fact, it's referred to as the spring constant. And S is the stretch. So, for example, a force of 10 pounds stretches a spring 3 feet. So according to this, the force equals Ks. Weight is the force, 10 pounds, 10. K, of course, is my constant that I don't know. And then S, the amount of stretch, is 3 feet. So this tells me that K equals 10 pounds divided by 3 feet. So 10/3 pounds per feet is the spring constant in this particular case. Now, if the mass, or if the weight, is hanging freely, then we call that situation equilibrium. So basically what we have then here's our stretched out spring with the mass hanging there. And recall this length, the total length here is L plus S because we have the length of the spring not being pulled at all, but now you have the mass attached. It's going to stretch it a little extra distance of S. So the weight is not moving, but hanging freely. So there's no force or anything like that acting on it, other than the force of gravity trying to pull it to the ground. So this here represents equilibrium as it's just laying there. Basically what we're going to do is we're either going to pull on this thing in some way or we're going to push on it. And whatever we do, we're going to stop. We're going to either pull or push, move out of the way, and let it bounce up and down, up and down, up and down. And that's the motion that we're going to try to figure out in this section. So here's what we do. We introduce a coordinate system inside of the middle of the spring here. And it will go until you get to the top of the mass. And I'm going to let this axis be t and this axis be y. So the initial position then is a length of L plus S. Although you'll find out we never actually need to know L for anything that we're doing. We only need to know the stretch, how much it's stretched beyond its non-stretched, non-weighted position. Hooke's law in more of a vector format takes this form. Now that direction is introduced into this problem, we are going to assume that downward is the positive direction. And then upward is the negative direction. So that whenever it falls below the t-axis, that will be positive. Whenever it pops up above the t-axis, that will be negative. So with this in mind then, Hooke's law can be stated this way. Now that I've introduced this. Now the spring constant is never negative. In fact, it's always positive. I doubt you have any springs that have a zero. Y then, as long as y is going this direction, you'll have a positive force. So as gravity or whatever acts on this thing, the force of the spring will try to pull it up. That's why if this is a positive quantity and y is considered positive down here, the force would be considered negative because it is aimed in the upward direction. So the force, a vector, if you will, is aimed in that direction, and that has to do with the spring trying to pull the weight upward, while gravity acts to try to pull it downward. So just to make sure that this is completely understood, in a situation where I really have pulled this thing down, here's my mass, here's my equilibrium axis, if you will, and my y-axis will go right through there. Something like this is considered positive y, or y is greater than or equal to 0, because this distance is measured below the t-axis. But now if it's compressed some, you might have something like this. Here's our mass. Now, I'm measuring from the top. Just pick a spot. It really doesn't matter if you choose the bottom or the top, whatever. The stretch is going to be the same. I'll choose it from the top because I'm interested in the stretch of the spring. So in a case like this, where it's above the t-axis, here we will consider the y values to be negative. Y equals 0 corresponds to the equilibrium position. Let the weight just hang with no movement. Equilibrium, in fact. So this is equilibrium. Well, we have the one force that ignores any positive or negative. We know that the force that is trying to keep the object in place is K times S. This is equilibrium. However, we also know that if m is the mass of the object, so m is the mass, it equals m times g. In other words, I have that 0 equals mg minus k times s. G is, of course, gravity. Now, G is considered positive in this case because downward is considered positive. Now, suppose the weight moves up and down. So it's maybe it's pulled downward and released, and it starts to bounce up and down, up and down, up and down. Well, Newton's second law gives us this. Tells us that force equals mass times acceleration. Or in our version of acceleration, force equals mass times y double prime. Remember, first derivative is velocity, second derivative is acceleration. So the total stretch then, if it's pulled to some point y, or even compressed to some point y, what we have is the restoring force of the spring will be this part. Y is going to be any addition to S that we have. Or Y could even be negative, and it will be slightly less than stretched out. So it can go past the S threshold, if you will. Let me come back for just a second. Let's go back to equilibrium. Here it is right here. I'm not really interested in the L part. But if y is any amount that is extra or any amount less, so if m is up here, say, y will be negative. If m is down here, say, y will be positive. So s plus y will be the total stretch of it. So that's why you have y plus s. Of course, the force wants to act upward, so that's why we have the negative. Now, the total net forces acting on the body then is, this is the spring, that part, and this is gravity. So the spring, the force of the spring is trying to pull it upward. But gravity is trying to pull it downward. Well, if the item is held in place, or actually at any time, say you froze the sight of it at some stopping point in motion while it's in motion, these forces are balanced out. So this whole thing will equal 0. But let me go ahead and multiply this through. Negative k times y minus k times s plus mg. And of course, we already know that the negative ks plus mg is equal to 0. So I'm left with force equals negative k times y. Now, force, I'm going to use the other version here, my double prime. and then add ky to both sides. My double prime plus k times y equals 0. And from right here, this is a differential equation that we can solve. Now notice m is mass, not weight. Weight and mass are not exactly the same thing. Mass is an invariant quantity. No matter where it's at, the mass is the same. Weight will depend on whatever gravity is. And we're going to do both English and metric, so this g will either be 32 or 9.8, depending on the situation. All right, as an example, a force of 400 newtons. So when I say a force of 400 newtons, I'm talking about weight, stretches a spring 2 meters. So for this part, that will allow me to find the k. Now then the rest of the problem goes like this. After we figured out what the spring constant is, now we'll start using the spring. So then a mass of 50 kilograms is attached to the spring and released from equilibrium with an upward velocity of 10 meters per second. Determine the equation of motion. So determine the equation of motion for something like that. Well, the first thing we want to do is figure out k. So I'll use this first part. I know that from force equals k times s, the 400 newtons stretches the spring 2 meters. So this tells me that k equals 200. And if you want units for this, newtons per meter. Now that I have that, now let's look at the equation of motion. So for the motion part, we have m equals 50 kg. We already know the k. So that tells us that when I do my double prime plus ky equals 0, I'll change the m to a 50. The k I already know to be 200. And then to solve this, since I am using m for mass, I am going to use r in my auxiliary equation, just so we don't confuse the m from the auxiliary equation with this mass m. So instead, I will divide by 50. So divide everything by 50. You get y double prime plus 4y equals 0. So the auxiliary equation will look like r squared plus 4 equals 0. Or r equals plus and minus 2i. So what that means is that y will equal c1 cosine of 2t plus c2 sine of 2t. And so to finish off this problem, I got to figure out what c1 and c2 are. Now, you're told that initially you are released from equilibrium. So released from equilibrium means that y of 0 equals 0. That's the equilibrium is the 0 position. So let me throw that into this equation. So y of 0 equals c1 cosine of 0 plus c2 sine of 0. Sine of 0 is 0, so I'm going to get 0 for y of 0. That'll equal c1. Cosine of 0 is 1. Well, that kind of takes care of that then. So my equation of motion now, since c1 is equal to 0, is c2 sine of 2t. Next, we had this. Released from equilibrium with an upward velocity of 10 meters per second. So what that tells me is that y prime of 0 equals negative 10. Remember, upward is negative. So y prime is the velocity and tells you negative 10 is the initial velocity set here. So I can take the derivative of our equation. Y prime equals 2c2 cosine of 2t. And then I'll go ahead and replace t with 0. I'll get negative 10 equals 2c2 cosine of 0. Cosine of 0 is equal to 1. So negative 10 equals 2c2. c2 equals negative 5. And so my equation of motion looks like this. Y of t equals c2, which is negative 5, sine of 2t. So there is my equation of motion. Now, some things you may be asked is, what is the period? Well, you probably know sine has a period of 2 pi. You divide by whatever number is in front of the t, so you get 2 pi over 2 is simply equal to pi. Another thing you might want to know is, what is the amplitude? And you always take the absolute value of the number right in front of sine. So the amplitude, the letter A is used for amplitude, is the absolute value of that number, or just 5. So if you were to look at a graph of this thing, well, actually, here's the way the picture works then. When we do equilibrium, that's where we start. So this spot right here is my L plus S. This is when t is equal to 0. So when t is equal to 0, we start the whole process off by hitting this underneath with a velocity that makes it 10 meters per second. Now the whole process, it goes up, then back down, and then back to the equilibrium spot in pi seconds. So let's see what happens at various places. Since I'm shooting it upward first, an amplitude of 5 means it raises to 5 meters. So the spring will be more compressed at that point. So it'll be raised 5 meters. When t equals, well, let's figure this out. Since my whole period is pi, this is going to be at its highest point, although be it in the negative direction, when this quantity in here is pi over 2, because then sine will be 1, and you'll have a negative 5 total. So if this has to be pi over 2, then t needs to be pi over 4. So pi over 4 seconds, we're up there. Then at pi over 2, we're a little more stretched. So this is at t equals pi over 2. We're back to equilibrium position because when t equals pi over 2, sine of 2 times pi over 2 is sine of pi, and that, of course, is 0. And then when t gets to 3 pi over 4, if I replace t with 3 pi over 4, I'll get sine of 3 pi over 2, which will be negative 1, times negative 5 will be a positive 5. So it'll be at the most stretched underneath. So this will be when t equals 3 pi over 4. This now will be 5 meters, but underneath of the t-axis. And then by the time we get back to pi, when you get to pi again, it'll be back to equilibrium again. Let's do another example. Example 3. A mass weighing 10 pounds stretches a spring 1/4 of a foot. So this first sentence will allow us to figure out what the K is. Next, a mass of 51.2 slugs is attached to the end of the spring. And then released from a point 1/3 foot above equilibrium with a downward velocity of 5/4 feet per second. All right, so to figure out the K value, I use the force of 10 pounds. 10 pounds equals K times the stretch, which is 1/4 of a foot. Make sure all your units are in the same. So if I'm dealing with pounds and feet, make sure everything's given in terms of feet. So I'll multiply through by the 4, and I will get K will equal 40 pounds per foot. Oh, I made a mistake in this part. Let me go ahead and clear it up now. Weight of 51.2 pounds is attached to the end of the spring. Now, for my thing here, I need M at Y double prime plus K times Y equals 0. I need to get the mass, not the weight of this thing. So the way to get the mass is to note that force equals mass times gravity. So in my case, I have 51.2 pounds equals mass times gravity in the American system of measurement is 32 feet per second squared. So I'll divide both sides by 32 and I get my mass equals 1.6 slugs. That's how mass is called in the American system. So let me go ahead and put my 1.6 in front of y double prime. My k was equal to 40. And then I'll divide by 1.6. And then finally I'll go ahead and solve this. The auxiliary equation is r squared plus 25 equals 0. So r equals plus and minus 5. That means my equation of motion is this. Y equals c1 cosine of 5t plus c2 sine of 5t. So that's the equation of motion. Now, I got to figure out c1 and c2. All right, so the first thing we were given is that it was released from a point 1/3 above equilibrium. So released at 1/3 foot above equilibrium. So that tells me that y of 0 equals negative 1/3. Up is negative. So let me plug it into the equation of motion. So y of 0 equals c1 cosine of 0 plus c2 sine of 0. Of course, sine of 0 is 0. And I have negative 1/3 equals c1. So far my equation is y equals negative 1/3 cosine of 5t plus c2 sine of 5t. Now I want to go figure out the c2, and that is usually given to us through the velocity. The initial velocity is 5/4 feet per second downward. So that tells me that y prime of 0 equals positive 5/4. So let me go ahead and take the derivative of this equation of motion and then set it equal to 5/4. So y prime equals, so I take the derivative of cosine, I'll get negative sine. I'll end up with positive 5/3 sine of 5t. Over here I'll get plus 5c2 cosine of 5t. And then I'll plug in y prime of 0 equals 5/4 to get the equation 5/4 equals. Once again, when you plug in 0, the sine disappears and you'll just get the cosine term, which will be 1. 5c2. Divide by 5, and it looks like 1/4 equals c2. So our equation of motion then is negative 1/3 cosine of 5t plus 1/4 sine of 5t. Now, some of the questions you could be asked here are, what is the period? Well, that's easy. Both of these have a 5 in front of the t, so both cosine and sine have period 2 pi divided by 5. The amplitude is a little more complicated. There's a couple of ways you can do it. If you graphed this thing on a graph, what you would have is something like this. Remember, it was released at a point that was 1/3 above equilibrium. So the graph will start up here, but then it will start to go like this. And there's an algebraic way to make it into a sine curve. It might go up a little bit more there. Just depends. There's an algebraic way to turn this into just a sine function itself. I'm not going to bother with that. What I'm going to do instead is I'm going to take the derivative and find where the highest point occurs, and then that will be my amplitude. So what I'll do is I'll set y prime equal to 0. Tells us where the min and maxes will occur. So let me go ahead and take the derivative of y. There's y right there. When I take the derivative of cosine is negative sine. So once again, I'll get 5/3. Y prime will equal 5/3 sine of 5t. And over here, I'll get 5/4 cosine of 5 over t. Of 5t. And we'll set that equal to 0. I'll subtract the 5/4 cosine, so I have 5/3 sine 5t equals negative 5/4 cosine of 5t. I'm going to divide both sides by cosine of 5t. So I get 5/3 tangent of 5t equals negative 5/4. And then I'll multiply both sides by 3 over 5 to get tangent of 5t equals negative 3/4. So if I want t, then I'll have to do the arctangent. I'll have 5t equals arctangent of negative 3/4. And then I'll divide by 5. So t equals 1/5 arctangent negative 3/4. You should know that when you take arctangent of a negative number, you will get a negative number. So in particular, the t value I'm finding will correspond to some location to the left of 0. So let's go ahead and plug it into the original function. So our original function was y equals negative 1/3 cosine of 5t plus 1/4 sine of 5t. I'll replace t with this quantity. So I will get negative 1/3 cosine. Now notice that the 5 in front of the t will cancel with this 1/5, and you'll get arctangent of negative 3/4 plus 1/4 sine of arctangent of negative 3/4. I'm going to do a little bit of arithmetic here. Arctangent is an odd function, so I can pull the negative in front of it out. So I'll have negative arctangent of 3/4. On the other hand, I'll have 1/4. I'll do the same thing over here, sine of negative of arctangent of 3/4. And then cosine is an even function, so it can squash that negative. Sine, though, is an odd function, so I'll pull the negative in front. The good thing about doing this is now I'm dealing, arctangent will be positive, so it will output an angle in the first quadrant. Well, sine is positive there, and so is cosine. So what I can do is this. If I let tan inverse of 3/4 equal theta, then I know that tangent of theta equals 3/4. So what I can do then is draw myself a triangle. Since this is all for first quadrant stuff, this triangle's fine. Tangent is opposite over adjacent, so I'll put a 3 here and a 4 here. And everybody knows on these triangles, this side is 5. Theta goes here in that corner. So cosine of theta is equal to adjacent over hypotenuse. Sine of theta is equal to opposite over hypotenuse. So this equation right here, that'll be 1/3 times, this is cosine of theta. So that'll be times 4/5 plus 1/4, that's minus 1/4, times 3/5. And I made a little mistake here. This negative does not come out front and cancel. That's still there. Let me put it back. All right, so I get negative 4 over 15 minus 3 over 20. Well, if you simplify all this, this is negative 5 over 12. So this represents, since it's negative 5 over 12, this represents as high as the graph will be. So let me draw another picture of this graph. And so when t is equal to arctangent of negative 3/4, wherever that might be, the highest point here will happen at 5/12 of a foot. And then it'll go and do this kind of stuff. And then when it gets back to the starting, when it gets back to this, whatever this was arctangent of negative 3/4. That's that spot right there. The spot where it gets to the highest point again will be arctangent of negative 3/4 plus 2 pi over pi, because that represents the end of the period. Now all of this stuff, this is all happening without any external friction. So like it's in a vacuum. Think of it that way. So the point is, this will just bob up and down forever. It won't have air resistance or anything like that dampening it. So this is, if I have the time, I'm going to do the version that involves damped motion. But right now, this is all freely undamped motion.